the proof of a theorem which was partly due to some technical ignorance of myself. So I will repeat the theorem and its proof. That's, I think, the best thing to do. The title was The Motion on Manifolds. And we know about the Lagrange equations of first kind. Which read m x double dot plus some lambda I is equal 1 to s d g I d1 gi of x to dm gy of x plus f of x, and g short writing meaning gi equals to 0. What are those numbers? S is the number of the constraints, of the functions, of the components of the vector G. M is the dimension of the underlying space in which the whole thing is moving and in which the manifold M is defined. That's the definition of the manifold. F is the force given function on Rm. F lambda I and xi are unknown functions. They have to be determined from this equation. Oh, there must be some equality here. Here. Excuse me. So that's the setting. And we use the regularity. Or we assume it. Which means that the gradient of this map has maximal rank. This gradient, G, is a matrix of type S times M. It has S rows and M columns. Rows count the components of G, and columns count the components of Rm, with respect to which you differentiate. And the meaning of this is the mass mass is a matrix. Typically a diagonal matrix with positive entries. But it may be also be a general positive definite matrix. Or for that matter, we could after allow some more general assumptions about M. For example, to be singular. So what is the meaning of this? The meaning is the mass times the acceleration is equal to force, but there are some unknown forces acting, and these forces are due to your constraints to move on the manifold. Those forces are orthogonal to the manifold. That's what stays here. This is the components of the normal vector to the manifold. Those forces are unknown except for their direction, that's known, but their size is unknown. And that's lambda I. And this should be then determined through the extra information of the constraint. So you have all together M equations here, M, and S equations here. And unknowns just as much as this. The components of X and the lambdas. So the sort functions are xy of t, and lambda I, lambda j, equals lambda j of t. Sometimes you will put them in a vector when using matrix formalism. Okay. That much for the setting. I think that's not bad to repeat it once more. We had, yes, we'll come after to an example. To a better example of this, but that's a general setting. So, what's the method? The method is to eliminate superfluous coordinates. In fact, this is a motion on an m minus m dimensional world. On the surface. And the surface has the dimension m minus s. And we know that in simple examples, we did it already, you can eliminate the constraints, get standard equations, and solve them. Well, the general method does the same in a theoretical way. This way will not be practicable for numerical computations, but it is to establish a theory. So, we consider a special case in which F is equal to minus gradient of a potential energy. We will assume those functions to be sufficiently smooth. Typically twice continuously differentially. So that's what I mean by the word smooth. So it is a smooth manifold, a smooth function f, and so on. So there is a theorem now, which which I now repeat. Let the function x of t be defined vector function such that it takes the values on the manifold, which is embedded in our Rm, and the function, the variable t is defined on an open interval AB. And let omega 1, which contains alpha and it maps into P of alpha, be a parameterization of the manifold for which we know to exist. Such that the values x of t are covered by the parameterization. That means you have a movement and on the manifold, and you have parameterization which covers this one. Then there exist twice continuously differentiable functions alpha 1 t, alpha m minus s of t, satisfying Lagrange equations. I write it down in a symbolic way. d over dt partial dl over d alpha dot I minus dl over d alpha I equals to 0. Where can you see this? Is that covered by the camera? Okay. Where L is equal to difference between the kinetic and potential energy, but written in new coordinates. That means T hat alpha dot equals to 1/2 x dot p of alpha t m x dot p of alpha. Well, let me put this dot here. Because there might be some misunderstanding. If you put here x dot, then you mean compute x dot and substitute p of alpha in it. But it's different, that you have p of alpha and alpha is function of t, and then differentiate. If I would write down all these dependents, you will get very, very clumsy formula. So this formula has to be understood properly. You may ask, what do you mean differentiate with respect to a velocity? Because this is a velocity, it is itself a derivative. But it is a symbolic way to write down very complicated formula in some compact way which can be well understood once you know what is meant. Well, so you can compute this, and this gives that's what it is. See, the only point here in doing this differentiation is that m does not depend on time. It's constant. It's a metric which is constant. And okay. And I will now rename this, give this a new name. Alpha dot t m hat of alpha times alpha dot. And use this vector notation throughout, writing alpha as a vector, column vector, and so on, as I did here with G and so on. Okay. So that's what T is. And what's the, oh, excuse me. I mess the names for the potential energy. Sometimes I write down U, sometimes V, as do most books. So I will try to be consistent now. So now, what is V hat? Well, that's simple. That is V of P of alpha. So now you know what this is. And this is understood that you consider your L as a function of how many variables? Of R m minus s times R m minus s. So the first m minus s variables are the positions in parameter space, and the second m minus s variables are the velocities. And that's what is meant, I differentiate with respect to the positions or with respect to the velocities. That's just the names for that. So you have to differentiate this first, and then substitute alpha to be alpha as function of t, and then make the derivative. That's what is meant by this compact formula. Now for the proof. Well, first we have to take care about the existence and uniqueness of those functions alpha of t. Well, this is secured by our theorem about parametrization. We know the parametrization is a bijection. So, and it is not only bijection, but it's also bicontinuous. So those functions exist. There are twice continuous differentiability of those functions is also something to be proved. I will postpone this. I will suppose those functions. You have here x of t moving, and down there in the parameter space you have alpha of t producing this. X of t equals p alpha of t. Now, the fact that this is twice continuously differentiable is a technical matter which I will not touch in this moment. So now let's start with this equation. We can rewrite it in avoiding those lambda I completely. How? To write down m x dot minus f is orthogonal orthogonal to the tangential space of x. It's the equivalent way of writing this equation. More precisely, m x dot of t minus f x of t orthogonal to the tangential space on the point x of t. So in fact, formally we now have eliminated the constraints formally. Now we have now to compute what that means. This is equivalent to writing down m x dot x of t minus f x of t scalar product with a basis of this equal to 0. If I have a basis for t. These are the vectors dp or d alpha. I will put here, well, I take a matrix notation, so I put here transpose for scalar product. Alpha I, well, taking at alpha of t equals to 0. We have to be now precise. Alpha, alpha, alpha I. Oh. So we have now to compute those two terms. We don't need this. So. So I compute first this term. Minus f x of t transpose to dp alpha of t d alpha I is equal to, well, dv on xt transpose dp d alpha I taken at the point alpha of t. Well, that's easy. This is by chain rule, nothing else, but dv hat differentiate with respect to alpha I taken at the point alpha of t. That's just chain rule. Now the next term is this one. M x double dot of t transpose dp alpha of t d alpha I equals to, well, this has now to be differentiated twice, taking into account that x is given as x of t is equal as p of alpha of t. So we have to use chain rule twice. So that's d over dt m yes, m d over dt p of alpha t transpose d delta p and delta alpha I alpha of t. And that's equal to d over dt. Now we differentiate that the sum or j m dp alpha t d over d alpha I. That's this I here, it stays. But now dp d alpha j point. Once more, now we have to differentiate this one. Excuse me. Minus. I will explain after. Let me write down the formulas first. So That's here. Yes. Minus sum over jk m dp. I will now skip this dependence alpha of t, write down just p as I did here, to be shorter. dp d alpha j d double derivative so let me first say that's the first, that's this one. Mx, okay. This is one line too much. No, that's correct. Use the Leibniz rule to differentiate this product and you get those two. So that's what it is. Okay. So we have this one. And then yes. We have to compute those two once more. Okay. Yes. That's it. So this is then equal to t where's this one? This can be recognized as d over dt, d over d alpha I of 1/2 sum over j and k dp d alpha j m dp, this is transpose dp over d alpha k alpha j dot alpha k dot. You just differentiate with respect to these variables, quadratic function, differentiate, excuse me, gives a linear one. And that's what it is. There is something lacking here. Alpha j dot I, well, it is same here, alpha k. No, it's correct. So it's just recognizing what it is. Simple as that. And the second one can be in the same way recognized as minus d over d alpha j of 1/2 sum jk dp t d alpha j m dp over d alpha k alpha j alpha k in the same way. This 2 1/2 comes from the derivative of the scalar product. You get twice the same expression if you differentiate this scalar product. So, and that's then, if we recognize what it in fact is, this is our m hat. So this is then d over dt partial d over d alpha alpha I d alpha dot minus d over d alpha I d hat alpha dot. Well, now this can be rewritten as d over dt d over d alpha I dot of t hat minus v hat. Why? Because v hat does not depend on the velocities. It is only the function of the first ms minus s variables. Now, adding this part here, we get then so I raised my starting equation. Well, it's here. It's here. Plus dv alpha I equals to 0 symbolically. That's what it was. We have completely computed now the first term. Adding this one, you get then d over dt d alpha d over d alpha I hat over d over d alpha I again t minus v equals to 0. That's now equivalent. Well, it is a bit of formal computation, are the main theoretical ingredients, are the technical ingredients, are the facts about parametrization. How fine parametrization is and what it does. That it maps smooth functions on the manifold into smooth functions into the space of parameters. That's less trivial. The other direction is trivial, but the other one is less trivial. But it's technical. So what we have done here, let me just discuss it a bit. Well, we have got, let me write it down once more. These are the celebrated equations by Lagrange. L minus d r alpha I L equals to 0. Those equations, what are there? These are the standard ODE, standard differential equations. Let's look for it. This is some function of alpha I here. And this is this here. So let's write it down to see what it means. D over dt, dl over d alpha I hat is equal to d over dt. Now I write it down this way to show you better what it is. But those two ways are necessary. Both the way getting the compact form and the way going to show you what this mathematically means. So this is now a sum over j n hat alpha ij times alpha j hat. And that's then equal to sum over j n hat of alpha ij alpha j double dot plus sum over jk d m alpha over d alpha k alpha j dot alpha k dot. Well, so now what do we have here? We have here m hat of alpha times alpha double dot. It's just a matrix multiplication. Is equal to what? Well, to some function of alpha and alpha dot. This one and the rest. Some smooth of alpha and alpha dot. What do we know about the matrix M hat? We have some information on it. If this would be invertible, then we could write it down this way. And that's again some other smooth function of alpha and alpha dot. And this is a standard function, standard form of a system of second order, which we have solved already. And now what it is? It has a unique solution, maximal solution, provided the functions are smooth, which they would be. But now let's look about this m, alpha minus 1. Where is the definition? We have some definition here of this. Here. What's that? M is a positive definite matrix, typically diagonal matrix with positive diagonal elements. And now we have this expression here. This defines the matrix M hat as function of alpha component-wise. So, are there any suggestions why this matrix should be non-singular? Well, use what you know about those dp over d alpha I. This is a basis in the tangent space. That means that those vectors are linearly independent. So we have a linearly independent vectors u1 to u m minus s, and you form the matrix ui uk. This is the called Gram matrix, and it is positive definite. See linear algebra. Any, these are linearly independent vectors in the space of just any linearly independent vectors. And such matrix must be positive definite if the original was so. Even more, it can happen that the matrix M could be just positive semi-definite. Some masses may be equal to 0, for example. And this is a sort of compression of a matrix. Think of this. You have a positive definite matrix and you take a submatrix of it. That's what it is. Taking submatrix of a positive definite matrix stays positive definite. And it may become positive definite if the original matrix were only positive semi-definite. Okay, so that's okay. And if this is a smooth function, which it is, alphas, this is smooth, this is a function of alpha, if everything is smooth. Inverse function, inverse matrix of a smoothly dependent matrix is again smoothly dependent. So all this is smooth. So we have to do with a standard system of ordinary differential equations. And that's the merit of the whole derivation here. There is one more point which we didn't touch as yet. We could have many parametrizations of the same neighborhood in a manifold. Bunch of them. In each of them, this Lagrange equations have the same form. You form your L in the same way from the kinetic and potential energy. You have always the same form. Not the same functional dependence. No, that's different. But the form is the same. Of course, if you would read books on physics, they would insist on those equations not only as a theoretical tool, but also as a technical tool. Why? Because they almost use very limited systems of parameterizations which they need, like polar coordinates or elliptic coordinates or something parabolic, and that's end of it for practical purposes. We mathematicians use this more as a theoretical tool to show that our system of equations is solvable the same way as the ordinary differential equations. And we will continue looking at that in the same direction. So I will stop now and make a small quarter of an hour. Recite meni još jednu stvar.